everyone. It's a pleasure to be here. I'm Farinaz Koushanfar from UC San Diego. And what I'm going to talk about, as it was mentioned, is fast adaptive learning of miner extractable values. And this is a joint work with my great academic colleague, Professor Ari Jules at Cornell Tech, and a number of very smart graduate students at UC San Diego and Cornell Tech. Before I go forward, I have to make a disclaimer that despite both Ari and mine affiliation with Chainlink Labs, this work is done purely in the academic setting and is completely independent of the work going on at Chainlink Labs. Okay. All right. I just told you that we're a bunch of academics doing work, and as you can see, we are trying to learn miner extractable value. And as I was walking here, I was thinking, wait a minute, what will everybody think? What is the goal of my talk really? I just if you think this is an academic work, if you're really smart, you should really start your own mining business and try to use this algorithm that you have, which you think is learning the miner extractable values to make money, and everybody will be happy. I guess that's not exactly how we are thinking about the world. We really, as scientists and engineers, we really desired to quantitatively measure and study and see what can be maximally extracted. And I guess as a scientist, if you can't measure it, it doesn't exist. So really, we wanted to know how much we can get from here. I guess it's not a new news for people who are attending this conference that the decentralized finance applications are growing in popularity, handling billions of dollars. And this is, of course, powered in large part by the rise of smart contracts. And this is something that is exciting many of us here. The smart contracts have really changed the ecosystem of how things work. So they can interoperate very easily. They have modular structure. They can be basically put together as Legos, and they can thus enable a much richer set of applications. I guess you're all familiar with decentralized exchanges, and they can basically be, for example, aggregated together to for trade execution. You can combine flash loan with decentralized exchanges, with lending contracts that use decentralized exchange as price oracles, so on and so forth. And, with each new technology comes a number of problems that may have not been foreseen earlier, and this is no exception. There's really a lot of unintended behavior that we see, in the DeFi ecosystem. There is, all this exploits that is going on in millions of dollars. We've all probably learned about the flash loan attack, the lending protocols that lose funds, and this is an ongoing battle, really, for making sure that everything is trustworthy, and the integrity is really one of the main things that will draw users' trust to use these systems and to be operating in these systems. Okay, here's an outline for the rest of the talk. I'm going to talk about miner extractable values via an example. I'll talk about some of the previous approaches that have been there, and of course, we're not the first one to look into this problem, but we believe that it's always good to make progressively more steps towards quantitatively analyzing what is happening. We will be talking about the optimization module and the simulation module before I conclude the talk. Before I go into the technical details of what we are doing, I just want to tell you one thing, and that is, one of the things that is really cool about this project is there's a lot of work going on in trying to use learning for optimization. And that's basically what we are doing. The underlying engine for optimizing and extracting these values is based on sophisticated learnings that adaptively learns what is happening in the optimization domain, and thus gets integrated and can optimize the space to the best that has been seen. Okay, so informally, miner extractable value or maximal extractable value is the ability of miners and bots and validators to extract value by changing the order of the transactions, inserting new ones, censoring, reordering. And the EV is the value extracted in a given transaction sequence, and MEV is really maximizing that value. So as you can see here, it really lends itself to an optimization formulation function. It really is being used as a measure of crypto economic security because it's really the worst case adversarial advantage that they have to extract the maximal amount of value out of these. Okay, let me just go through an example to make it a little bit more clear. Here is a user who wants to swap 100 US dollar into ETH using a decentralized exchange, and executes a smart contract here. Now what happens is the ETH price is really what is defining the equation. Now the miner has this ability to insert or change the order of the transaction. What they're going to do is they're going to swap 10,000 USD into ETH, and all these is going to increase the price of the ETH. Then the user gets less ETH than it would because the price has increased, and then the miner is going to make a profit because they're going to use this higher price converted back into their liking. And this is called the sandwich attack, which has been studied well in the literature. There has been, because this problem is so important, there has been a number of approaches prior to our work. Most works, what they do is they take a specific attack, like the sandwich attack I was just showing to you, and then this, although has value, does not necessarily generalize to all different contracts or new methods of attack, transaction types that come in. And these approaches are not really able to find the worst case scenario in each and every setting for the adversarial advantage. In a prior work called Clockwork Finance from my collaborators at Cornell Tech, what they have done is given a set of user transactions and templates for these transaction insertions. They tried to find the optimal value of the inserted transactions and optimal order of transactions for maximizing MEV. They had some formal guarantees of the optimality of the obtained MEV, but there was one real big problem, and that was that it was not scalable to complex contracts such as the ones that contain loops or large number of transactions. So even though academically it was formulating the problem, it really did not provide a scalable, largely usable solution that could be used for for larger contracts and the ones that had loops and so on and so forth. So that's where we came in, trying to find how we can best optimize this complex space. So this led us to invention of Lantern, which is really a learning-based problem formulation and simulation framework. It's a native smart contract execution. It can generalize to any smart contracts by treating this bytecode as a black box simulation environment. And what that means is that, because, this is a contract and you can technically simulate it and learn it, any contract can actually be generalized into this black box setting. It is amazingly scalable. It can uncover MEV strategies spanning a large number of transactions efficiently and, without really trying to model things formally, like with formal verification and other tools that may not be scalable to everything that we see out there. We have achieved near optimality of the uncovered MEVs, and we actually have been able to beat the MEVs exploited in the wild, and that makes us kind of excited not because we're trying to beat them and exploit the system, but because we believe that we have new tools to learn how the system is functioning, and that can quantitatively help us to go forward with the science. So I'm going to just go through the system and technical details very briefly. For those of you who are interested, I'm happy to take questions, of course, later on, of course, and we will be having hopefully an archived version of this pretty soon. So given a pool of transaction and the current state, we automatically learn strategies to maximize the miner extractable values. So here we have the mempool transactions. There's a state for the Chainlink, and what happens is that we want to get the maximal MEV and optimized transaction sequence that maximizes the MEV. So what happens here is we are really inserting this learning-based black box optimization, which is providing a simulation environment. We give transaction sequences to this simulation environment, and as we give these transaction sequences, we measure this extractable value, and this measurement is actually not blind, it's learning-based. So as we learn more about the space of the optimization problem that we are dealing with, we are adaptively sampling at points that we do not see, and we believe we need to make more samples, and that very smart strategy of adaptively learning and optimizing really helps us to go through this optimization. Because of the constraints in time, I'm not going to go through this details of the simulator. It's basically, what I told you in a nutshell. It's a learning-based optimizer that, by simulation, learns what is happening in reality and, just outputs the maximal EV and an optimal order of the transactions that would maximize the miner extractable values. It has two hierarchical learning loops, the outer loop, which learns the optimal order of transactions, and an inner loop, which learns the optimal miner transactions. I'm not going to go through the details of the optimizer, and of course, the optimality, as I said, means a higher value of EV or MEV, but that is really for us to learn quantitatively what is happening here and try to really analyze it. And this is really empirically searching for optimal hypervalues. There has been a number of search space geometric visualizations that we went through, and challenges for the this optimization in general is that this is a non-monotonic optimization problem. There are high correlation between variables, and it's a high-dimensional space. So our optimizer, based on the adaptive sampling, takes into account all these parameters, and with that, we went through a number of evaluations, which I'm not going to go through in details, but I just want to conclude by mentioning that we have a really nice formulation for crypto economic smart contract security as a learning task, and the approach is generalizable to any smart contract by treating the smart contract environment as something that can be learned. So we use a combination of simulation and learning to learn the space of this optimization problem, and then adaptively scale to learn this MEV strategies in terms of ordering and in terms of the number of transactions. And it really beats what is available out there, and this is really helping us to quantitatively understand the space of EVs or MEVs, and to try to have better strategies to hopefully thwart them and avoid exploits in the future. With that, I would like to thank you all for your attention, and I'd be happy to take any questions.